This is a tutorial about properties of natural transformations as they are used in practice of programming. This is not about category theory, although the notion of natural transformations came from category theory, but I will only focus on the practical applications and on what a functional programmer needs to know in order to be able to reason about natural transformations. I will talk about how to recognize natural transformations, refactoring in code, and how to derive properties of natural transformations by symbolic reasoning. The motivation comes from a refactoring that changes the code without changing the result. One possibility is that, for instance, you have here a database access that gives you some kind of iterator or stream, and you want to extract user information from that stream as a list of some user information data. And you have two possibilities. You can first convert the iterator to a list and then convert the database rows into the user information values, or you can first convert to user information values and then the resulting stream converted to list. Another example is when you need to exclude some sort of invalid rows from the data. So you can first extract the user information and then you filter valid users, or you first filter valid users, which means you have to extract the user information inside the filter as well, and then you extract user information. So in both of these cases, the result is the same, and it is guaranteed to be the same. And the reason it's guaranteed is that this function, toList, is actually a natural transformation. It's a function whose type signature can be something like this. And this is a typical type signature of a natural transformation. The filter function, although it doesn't look like a function with this type signature, it's also actually a natural transformation. So natural transformations generally are, from the programmer's point of view, functions with a type parameter and the type signature of this sort, where you have a type constructor with a type parameter going to another type constructor with the same type parameter. And the usefulness of these functions comes from the fact that they satisfy certain properties. These are called naturality properties or naturality laws. And these properties guarantee that this is always equal to this, and that this is always equal to this. So naturality laws are more abstract expressions of this this equivalence, of the property that the programmer can refactor code in this way, and it is guaranteed that the result will be the same. In order to formulate these properties in a more rigorous way, we need to write equations. In order to write equations more easily, I will introduce a certain kind of shorter syntax, which is entirely equivalent to Scala code, but is much easier to work with. If you only occasionally look at such equations, then it doesn't matter if you use short syntax or a long syntax. But if you work with those derivations a lot, then the shorter syntax will save you a lot of time. And this is the syntax that I introduced, that I'm using in my book. not necessarily the short syntax you can find in other books or tutorials. I will only show certain definitions of the short syntax that I'm going to use in the next slide so that we can rewrite these properties as equations. So first of all, the type parameters, such as this a, I'm always writing as a superscript. I usually abbreviate type constructor names in some way if they're too long. So this is the syntax that is exactly the same as this Scala code. This is type signature in Scala. If I want to say that the values has a certain type, such as this function of a to b, then the short syntax looks like this. So I write this as a superscript but with a colon, which is different from this superscript without a colon. So this superscript without a colon is a type parameter, like this is a type parameter. And this is a type annotation, which just tells you what type a certain value has. And this I write like that. The map is a kind of lifting of a function from a to b. So if f has a type a to b, then this function, map f, has type list of a to list of b. And the short notation for that is this. So I have again a superscript, but I have an up arrow in the superscript, and I show to which type constructor I'm lifting. If it is obvious to which type constructor you're lifting, you can omit the type constructor name and just write something like this. But it is very helpful to write down the type constructor names. Very frequently it is confusing without those names, and it's much easier to reason about functions and function compositions if you have this information right in front of you. This is a typical way that Scala code composes functions, is a chain of functions applied one after another to a value. And I use the composition symbol, which is this, the fat semicolon, which kind of reminds me of the composition symbol that you can find in books such as this. This circle or fat point. But the composition I'm using is a forward composition. So I first apply this function and then I apply this function. So this semicolon is a forward composition. In Scala, this is the operation and then. And the fat point is a backward composition. So f before g, as you can read that, f before g is equal to g after f. So in principle, these are entirely equivalent, whether you write your functions like this, a composition like this, or like that. However, in many cases it's easier to look at the types of functions if they're composed in a forward composition. We'll see that in the next slide. So for instance, this is a chain of two lifted functions, and we know that this is equivalent to the lifted composition. In the short notation, it's written like this. It's a composition law of the functor list, or of any other functor would be the same law. So now you see how this notation helps you to see what can be composed, what can be lifted, shows you this is a list, this is another list, so you can obviously compose them together. They're lifted to the same type constructor, and so you can put the lifting outside of the composition. Now, using the syntax, we can write the previous examples. The toList function, which had this type signature, is written like that. And the law that we want is that first you do a toList and then you map with some function, any function f that can be any function from type A to type B, say. And these transformation toList and then lifting f is the same as first lifting f and then transforming toList. So we expect this to work because the transformation toList doesn't change any values, it just rearranges the data. So the data was in a stream, it accumulates this data into a list. So it doesn't matter if you first map with some function f or you first transform toList and then map to the function f. It doesn't really change the result. So this is our intuition, this is our expectation about the function toList. But we would like to write this expectation as an equation so that we can quite rigorously check that this expectation is valid. And the equation can look like this. So first you do a toList with a type parameter a, and then you lift the f, which gives you a list of type b. So now the type diagram helps you to see that you are first you go from a stream of type A, then you get to list of type A, then you get to list of type B, or you first transform the stream to a stream of type B by lifting the f to the stream, and then you transform that to a list. So this diagram, which I call a type diagram, it's just helping you to see what types are being used at every point of this equation, but it's exactly the same as this equation. I have written the types here, the A and the B, just because in Scala you can write these types. You can write your code with toList of A. For example, you can write a code like that if you wanted, but usually the type annotations are not necessary. The type parameters can be found automatically by the Scala compiler, so usually you do not write them. And so the equations also could be written with or without these explicit type parameters. It's the same code. So just to remind you that equations are actually just code. This code, which in Scala is this, always gives the same result as this code, which is in Scala that. And I would write this equation as toList f map equals f map toList. However, now this is very terse and it does not show you what types are being used, and this f is lifted to the stream or to the list. You don't see that. So this is you don't see also what type the data is. So this toList is with type A, and this is shown here but not shown here. So it's up to you what you choose to write when you write these equations, or what you choose to omit. What I usually do is I write the type constructor names or the functor names, but I do not write the types. So usually this is sufficient to write equations like this. Now we do the same thing for the filter. Filter has, say, this type signature, which I just chose to be curried for this tutorial. The function can be applied to a predicate, which is a function from A to Boolean. In the short notation, the Boolean type is just number 2 with some kind of fat lines. The unit type is number 1 with fat lines. So that is the unit type in Scala. And the 2 is the Boolean type. So we can then write this equation, which says that if we do a map and then filter, it's the same as when we do first a filter and then a map, although we have to now change the predicate, because the predicate will have the wrong type if you don't change it. As an equation, you write like that. So first you lift f to the stream, then you filter with p, or you first filter with f before p, so f is applied to x before p, and then you map with f, so you lift f to the stream. Now here it's always the stream functor, there's no change of the functor, so in principle I could omit this stream notation and just write f with up arrow for brevity. But this is not important. Sometimes it's too many things after arrows. In most cases it's not. In my practice, in most cases it's okay to write them. So we have seen these examples. They all look kind of the same in the sense that a transformation before map equals a transformation after map. So this before map, this after map. This before map, this after map. And every time you have this kind of diagram where the result is the same whether you go this way or this way. So these diagrams are called in mathematics commutative diagrams. And for programming, I would only use them to illustrate the types that I'm involving in my equation. So I will show at the end of my talk how equations are significantly better tool for reasoning than diagrams. So diagrams are useful to show the types and to look at the types to check that all the types match. Once you have checked that, you can stop writing these type annotations like these. In your calculations, everything is guaranteed to be fine since you checked the types. So let me go back to our main theme, the natural transformations. So this law, which is the transformation before map equals a transformation after map, is called the naturality law. And programmers' intuition about code says that this should work. This law should hold if the code is written such that it works in the same way for all types. So when a programmer writes code that works the same way for all types, that is expressed by the mathematical formula, such as this one and this one. So another example would be the head option function. Again, we have a map before head option and head option before map. So head option takes the first element of the list if it exists. If it doesn't exist, it returns an empty option. So Again, head option is consistent with our intuition that this transformation does not change the values, it just rearranges the values in a collection. So there was a list and there's an option. So there are some values in the list and there are some values in the option maybe, and they're arranged in a different way in these two collections, but the values are the same. And so you can transform these values first and then take the first element, or you first take the first element and then you transform, the result is the same. So another example would be reversing a list. So again, you can first map and then reverse the list, or you can first reverse the list and then map. The result is the same. Another example is the pure method, which is defined for a number of type constructors, which is a function with type signature like this, and I denote it with a short pu, which is helpful because pure is used a lot in derivations. And it has the law, which looks like this. You can take a pure and then you map, or you can take a pure of something where you already mapped. And as an equation, you write it like that. And so basically, it's always a law of this form. You change the order of application of some transformation T, which is in our examples to list, head option, reverse, pure. So let's call this transformation T. And you permute the order of application of T and of the lifted function f, map of f, where f is an arbitrary function. So T is a fixed function that is the natural transformation, such as this, and f is an arbitrary function. So in our first example, we had these getUserInfo functions instead of f, but f can be anything. It can be any function from any type A to any type B. So let us now formulate this in a general way. We have a function t that has this type signature. So I remind you that in the code notation, these are type parameters. So in Scala, this would be def t of a, f of a going to g of a. And this must satisfy the naturality law, which is first you lift to f and then you apply t, or you apply t before lifting f to g. So importantly, you lift to two different type constructors on the left of this equation and on the right of this equation. And this suggests a mnemonic rule that if you have this type signature, f going to g, then the lifting to f must be on the left and the lifting to g must be on the right. So, and this works very well with the forward composition, where you first apply this function and then you apply that function. So this is a general definition of a natural transformation. So natural transformation in a programmer's view is a function with this type signature, where f and g are certain type constructors that must be functors. It must be both covariant. They actually can also be both contravariant. It's still the same equation will still work. But in this tutorial, I will only consider the case when they're both covariant type constructors, so they're both functors, covariant functors. Many standard library methods in Scala have this form, have this type signature. For example, head option, last option, reverse, swap, map, flatMap, pure, and so on. Now, some of these methods have more than one type parameter. Note that here I did not allow for more than one type parameter. So the notion of natural transformation is relative to a specific chosen type parameter. If there are many, you need to use one at a time. So let's look at this example. flatMap, imagine it has this type signature, which I call FLM, which is a curried version of flatMap, where you have first the function of this type, and then the argument, which is in Scala usually the first one. So I rearrange the arguments a bit, but this is a much more convenient function to work with in derivations. So I call it FLM instead of flatMap. So what is FLM? In Scala, this type signature would be def FLM of AB, and then A to M of B, and then M of A, and then M of B. So if you take this function, you see it has two type parameters. So let's fix the type parameter A and consider B as the free type parameter. And then this type signature looks like some FB to GB, where FB is defined like this and GB is defined like that. And see, these are type expressions that are covariant in B. And so then it is a natural transformation with respect to the type parameter B. And similarly, you can formulate that as a natural transformation with respect to the type parameter A. Although then both of these would be contravariant in A, but that's still fine with natural transformations. So what is the naturality law for flatMap in this formulation? The naturality law always has this form, but the type constructors F and G are now defined in this strange way. No matter, we need to write down what is the lifting of some function to F and some function to G. Now if you write down what that must be, so F is a type constructor that is covariant in B, and you should be able to lift to it any function. So then if you write down what it is, you get these expressions. It's a function from some P of this type into a composition of P with the F lifted to M. So let's say F is a function of type B to C. Then this will have type FB to FC. And indeed it has this type. And similarly here, for this other type constructor that I defined. So the result is that if you substitute into this law the code for the lifting of F, then you see FLM is applied to the first argument, but the first argument must be substituted with this. So then you have this formula here, you have to put it here. And the second one, you do not change P, but you have to post-compose, you have to compose with this, and this adds you the lifted F. So then you have this law, which does not look like this law on the surface, but it is actually in disguise. Once you substitute this code, and once you define FLM as a formally natural transformation between functors F and G. So let me look at some more practical uses of natural transformations. So we have seen that refactoring can be useful, but before you refactor, you need to recognize that you're dealing with a natural transformation. So refactoring of a map and natural transformation will be then clear. And how do you recognize? So here's an example of what I would do if I saw code like this. So suppose I have some kind of function that has argument of this type and argument of that type. So it's some kind of name that could be present or absent, and an ID is always present. And I want to make sure that the name is present, and if it's not present, I want to return empty option. So I want to return this as a result. So it's easy to implement this function. I just map on this option and construct the pair like this. But now I look at this code, I recognize there is nothing specific about the types string and long in this code. So this code would work exactly the same way if I introduce type parameters a and b instead of the types string and long. So now I refactor this and I get exactly the same code working for arbitrary type parameters a and b. So now this type signature has the form of natural transformation if we fix the type parameter b and we define the type constructors f and g like this. We don't have to do this in the code. We can just write down as a comment that this is now a natural transformation. But in order to make sure it is a natural transformation, we write maybe by hand, we write these code formulas. Consider B a fixed type. Option of A is denoted as 1 plus A, is the short code type notation for that. And then you look at it and you say, yes, indeed, it's covariant in A, covariant in A. And so indeed this is a functor, covariant functor in A, this is covariant functor in A, and so it's a natural transformation. You need to check the naturality law. But actually, we will see later that there are general constructions for natural transformations, which you can prove once and for all, and then you don't have to check every time. It's made out of option, pair, and all of these things preserve natural transformations. So you don't really need to check the laws by hand in every such case. And the same thing would be if you consider A as a fixed type, then you define some K and L as functors of B, and again you have a natural transformation with respect to the type parameter B. So now out of this code, you have refactored into a natural transformation with two type parameters, which is natural with respect to A and it's natural with respect to B. So later you could do a map on it, you could define refactorings that you know will be correct. Another example is, now you had this previous situation, but now you have a list of those. So you need to transform a list of this pair of option A and B into a list of option of pairs AB. Well, you just do the same as before, except you map over the list. So you repeat the code from the previous slide, but this must be B. You repeat the code from the previous slide, put it into a map, and you're done. And you're also guaranteed that this is a natural transformation. You don't have to check the laws. Why is that? Because it's a general construction. If you have a functor f, which is in case that I just looked at, it's a list, have a functor f and you have a natural transformation between some g and h, then you can compose the functors and you have a natural transformation of this kind. So let me help you see the Scala signature for this. It would be f of g of a going to f of h of a. So the short notation puts a in a superscript of g and puts g of a into a superscript of f. And in this way, it replaces these nested brackets in Scala. So in our case, f is list, ga is this, and ha is that. So as I said, option is 1 plus a, option of a, and the pair is the product. So this is a product type, and this is a coproduct or disjunction. The type notation of this kind is designed to help us recognize type equivalences. We can just use the rules of ordinary algebra of polynomials, which we hopefully still remember from high school, and then we just transform this into this by expanding parentheses, and then 1 times b is b. So these are valid type equivalences, which we can see right away once we have rewritten the types in this notation. So this is why this notation is helpful. Another example would be to have a list of the pair of trie of a and b, which we want to transform into this. We can just use the same code because trie also has the map method, just like option does. And we can check that this is a natural transformation. To ensure that this is so, we first write it in a type notation where the trie is e plus a, where e is the type of the exceptions. And then you have this formula, this type formula. So basically, let me just indicate that e plus a stands for either of e and a, and the trie type can be seen as an either of throwable and a. It's equivalent to that. So you can write out the naturality law, of course. Let's prove that this is so once and for all, that if you have an arbitrary functor f and an arbitrary natural transformation ga to ha, then you can also implement a natural transformation of this type signature by just putting a map on top of that natural transformation. So let me write a derivation. So I have given a natural transformation t, which is ga to ha, and given a functor f, I define the natural transformation u, which has a type signature fga to fha, and I define u as t lifted to f. Now I need to prove the naturality law. Which is that for any function f of type a to b, I must have f lifted to the functor f g. So this functor f composed g is in Scala, this would be f of g of a. it's the same as f superscript g superscript a. So I lift to that functor because it's on the left of u, and then u must be equal to u and then f lifted to f compose h. Now the lifting of f compose h, so this is the law that we need to check. The lifting to f compose h is easy to define. The programmer can just look at this type and understand how you lift. You first lift to g, and the result you lift to h. So you have a Scala code that look like .map of f. That's what you would write in Scala to do that. But in the code notation, it is helpful to be more explicit as to what you're lifting to, because in Scala you just write .map, and you don't know what you're mapping to. You have to look at the type before you remember that. When you do calculations symbolically on paper, it is helpful to write out the types of the type constructors that you're using. So that would be f first lifted to h and then lifted to f. So let's substitute this over here. So we have f lifted to g and then lifted to f, and then we have u. So I have written this. Now I'm writing u. U is t lifted to f, and this must be equal. We don't know, but we should prove that it is equal to u, which is t raised to f, and then f lifted to h lifted to f. Now, if you look at this, you recognize that this pattern here, it is something raised to f, something to f. So this can be simplified as the composition law, which I have shown in one of the previous slides. So this is equal to the composition of these two functions lifted to f. So then I have done this, and the same I do on the right hand side. And now you see how helpful it is to write the type constructors that I'm lifting to. F and f, I see right away that I can pull the composition under the lifting. Would be less clear, but we have to believe that this is so and check the types every time you do it. Now you'll save time. Now, by assumption, T is a natural transformation. So T already satisfies the naturality law, which is naturality law of T. It is f lifted to g, T equals T f lifted to h. And this is exactly what we have here. And so all it remains for us to do is to raise both sides of this to the functor f. And we get this equation. So we have proved the naturality law for the natural transformation u. So then this is a general construction that we don't have to prove every time. And the result is that whenever we have this kind of situation, we know that it is a naturality law that automatically holds for this natural transformation. Another example is the function that calculates the length of a list. It has this type signature, and at first sight is not of the type required for natural transformations, but we can easily put it into that form, into this form, if we define the functor g to be always a constant type, the integer, regardless of the type parameter a. So this is called a constant functor. And sometimes this is also called a phantom type parameter, so that this type parameter in G is not actually used anywhere, but it's still there formally. And if we write down the naturality law for this function, we'll get this equation, which is a general naturality law. But in this case, the G is a constant functor and does not change this value ever, because you map with some function. This must be a lowercase f. You map with some function f from type A to type B, but these types are not used anyway, so this integer value doesn't change. So this is an identity function. So this is an identity function, so the result is this law. Now this law means that the length function, it gives the same result if you first transform the values of the list in arbitrary way, and then you compute the length. And you can, for example, choose the function f as a constant function, which always gives the same result. Still, the length is the same. So the length of a list does not depend on the values stored in the list. And this follows from the type and from the naturality law. So this is guaranteed if you have any function of this type, whether it computes the length of or not, its values will not depend on the values stored in the list. So that is an interesting fact, that the naturality law gives you already some important information about the behavior of your function, even though you have not ever actually examined the code of this function. Now, these are practical examples that you could use in your coding. Naturality laws and natural transformations have other uses in functional programming which are less directly related to everyday coding. But sometimes they're important when you're writing new libraries, especially libraries that have new type classes, or implementing existing type classes for new data types. One example of using naturality that I'm going to show now is how you can simplify the definition of the pure method. So a number of type classes require this method. So for example, monad and applicative require this method. And this method must be a natural transformation. So the naturality law is illustrated by this diagram. And it's written like this. So now, why is this over the form fa to ga? It's because instead of fa, we just write a, which is the identity functor. So we define fa to be a, and that's the identity functor. So then, lifting to the identity functor is just the function f. And that's why we have here the function f, rather than the function f lifted to something. But this is, formally speaking, this is lifted to the identity functor. So then the naturality law for the pure function is like this, the method pure. We can use this law to simplify the pure function, to reduce it to a simpler value. Here is how. We are allowed to use this law for any a and b. So let's set a to be the unit type. Now the unit type is denoted by this 1 with fat lines. The unit type has only one value. This value I denote by just 1 without fat lines. And we are free to set a type A to anything we want, for example, to the unit type. So we can also choose the function f in any way we want, because this law should hold for any f. So let's pick a value b of type b and choose the function f to be a function that takes a unit value and returns this fixed value b. Let's put that into the naturality law. So in the code, we will have this. In the code notation, we will have this. So we have just substituted this f, which is this function, and this pure method is acting on the unit type. So actually, it is on the unit type. There's only one value of the unit type that we can start with here. So its value is in Scala denoted by the empty parentheses. It's the same as the number 1 without fat lines in my notation. So then the naturality law looks like this. We have a composition equal to composition. And if we write down what that is, in Scala it's like that. So the result is that the function pure applied to an arbitrary value b is always equal to this. And this is a function pure applied to the unit value, the empty parentheses. So to write this in code, pul of b is always equal to pul of 1, to which we apply the mapping of 1 to b lifted to the functor L. Now this little triangle means substituting values into functions. So then I will not use this notation very much in this tutorial, but this is a very useful notation. This triangle operator, which in some languages is even defined as a standard operator. So let me write what it is. So x triangle f is the same as f of x. So in Scala, this is, for example, x dot length. And that's the same as x, and then triangle, and then length. So let me then continue. We have expressed the function pure for an arbitrary value b of arbitrary type b through a fixed value, which is the pure of the unit. And then this is a code which lifts something, but this is always the same. So in other words, given any value of this type, which is a type of L of unit, we can lift it with this and we restore the entire function pure. So the entire function pure is restored from a single constant value of this type. Moreover, if you define pure in this way, it will automatically satisfy the naturality law. Now, I will not necessarily prove that right now, but this can be proved really easily by writing down the naturality law. So if you define your function pu like this, and then you substitute it into this naturality law with arbitrary types a and b, then this just falls out and you have functor composition, and because of functor composition, this just works automatically. So this makes pure equivalent to a single value of this type, which I called wrapped unit. So it's a unit value wrapped into the type constructor L. So it's a wrapped unit. And this can simplify the definition of the type class. Let's say that there's a pointed type class with the method pure, or monad or applicative type class that have this method. Instead, we can just require to define this one value of type L of unit, and then we can restore the pure method out of that automatically without. So it's much easier for the user to write a definition of this. It's just a single value of, for example, for option we have this, for list we have this. We can just store this value. Doesn't even have to be a def in Scala. It could be a val in some cases. So it could even give you some advantages sometimes. And the law, the naturality law, will be automatically satisfied. A similar reasoning is about the equivalence of flatMap and flatten methods. So these are the standard methods for monads. For collections in Scala, most collections have these methods, but they are equivalent. So and at first you would think it's strange that they're equivalent, because flatten has, let me write down the type signature of flatten, which I denote simply by ftn. It has a type signature of m of a to m of a. So in Scala this is def flatten of a, m of a going to m of a. Now, how can it be that a function with this type signature, which has two type parameters and a much more complicated type signature, is equivalent to a function with this much simpler type signature? And the reason is the naturality law for flatMap. This naturality law looks like this, and it allows us to express flatMap from a function composition through this. Now the type diagram illustrates how it works. So you start with some value m of a, you lift to m of b, and then you do flatMap. Or you do directly flatMap with this function, which has type a to b and then b to m of c. So this is, in total, this composition has type a to m of c. Now you see how easily we can find what types functions have. So we just look at this composition, we come from a to b, and then from b to m of c. So obviously we have all the types here checked, and they all match. The flatMap is expressed through flatten like this, or in the formula it will be written like this. I should, for consistency, I should write G here instead of F, because F I've used over here as a function of a different type. So we can also express flatten through flatMap like this. It turns out that as long as you assume this naturality law for flatMap, then these functions are equivalent. So this is a very non-trivial thing. So let me see how I can try to prove that. So first of all, flatMap of G is defined by G lifted to M and then flatten. And flatten is defined as flatMap of identity. And additionally, I have the naturality law, which I have right here. FlatMap fg equals f lifted to m flatMap g. In order to show that these functions are equivalent, what I need to do is I need to show that if we take, say, a flatMap function that satisfies the law, and we define the flatten function out of it, define flatten as this flat map of identity, and we define a new flat map, which I call flatMap prime, using this first equation. And the flatten was just defined. So this is GM, flat map of identity. Then flatMap prime must be equal to flatMap. So if we start with any initial flat map here that satisfies the law, then we define flatMap prime through these equations, and we get back the initial flat map. How do we show that? Well, let's find out what is flatMap prime of some g. It is g lifted to m, and then the old flat map of identity. Now if you look at the naturality law, this is like the right-hand side of the naturality law, where instead of g we have identity, instead of f we have g. So this is therefore flat map, which we assumed satisfied the law of g semicolon identity, but that is clearly equal to flat map of g. So for any g of type A to MB, we have proved that the new flat map is equal to the old one. And secondly, we have to show that if we start with some flatten, define flat map out of it in the same way as before, then define a new flatten prime out of this flat map that we just defined. Then we need to show that the new flatten is equal to the old one. So how do we show that? Flat map of identity, we substitute in here, is identity to the m, flatten. Now identity lifted to a functor is still identity. This is the identity law of the functor. So this is identity flatten, this is equal to flatten. So in this way we have shown that the functions flatten and flatMap are equivalent, assuming the naturality law. Now without that assumption, of course, they're not equivalent. There are many more functions flatten with this complicated type signature that may not satisfy the naturality law. But once we assume naturality law, then flatten is equivalent to flatMap. And actually, we can also show that if flatMap is defined through flatten, then this flatMap satisfies the naturality law. We have to show that because we want to show that all functions flatMap with naturality law are equivalent to all functions flatten. So if we have some arbitrary flatten and we define flatMap from it, we need to prove that it satisfies always the naturality law. So let's check that. So flatMap flatMap of fg. I'm not writing any types here because we already checked that all the types match. You don't have to write types. I just write the functions. Now this is fg lifted to m flatten, and the right hand side of the law is f lifted to m flatMap g, and that is equal to f lifted to m g lifted to m flat. So clearly this and this is the same because of the composition law of the functor m. So then these are equal. So we have shown that some natural transformations are equivalent to some values. These equivalences can be generalized. So instead of these natural transformations, which are the pure methods, being equivalent to the set of all values of type L1, which was the wrapped unit. In Scala, this would be like this. We can generalize to any type Z, any fixed type Z instead of unit type. And in order to generalize this, we have to replace this A by a function Z to A. Now, if Z is unit, then this is the same as A, equivalent to A. But generally, we can replace it like this and generalize. So that's what I would like to show now. It is called the covariant Yoneda identity, that the set of all natural transformations of this type signature, so this is one functor and this is another functor, is equivalent to the set of all values of this type. Now, for notation, it is useful to indicate that A is a free type parameter of the natural transformation, but Z is not. So Z is a fixed type. So to indicate this, we write the explicit type quantifier for all A. So this is for all A. And then some type expression. We write it explicitly. So the result is that what we already showed for the pure method was this, that all natural transformations of this type signature are equivalent to this value. And the generalization is this. So all natural transformations with this type signature are equivalent to values, or all values of this type. So to prove that, we need to do a similar thing to what we just did with flatMap and flatten. We need to implement the equivalence or the isomorphism, to use the different word for equivalence. So we need to implement two functions. One function will go from this to this. Another function, Q, will go from this to this. And then we need to show that the composition of these functions is identity. So let me prove that. So first of all, we have the function p, which goes from for all a, z to a, la, where L is some functor, going to LZ. Q. So how do we implement this function first of all? Well, so this P is a function of one argument. Let's call this argument Y. And this argument itself is a function which has a type parameter A. So this Y in Scala, this will be some def Y of A, right? Now, we can call this function Y with any type parameter we want, because this function is defined for all types A. Let's call this with type parameter A equal to the type Z. So we define P as Y going to, so it's like a Scala code, def P equals Y going to, and then we need to return a value of type L of Z. So let's compute a value of type L of Z by calling Y of a function. So first of all, let me indicate here type parameter Z, and then the function Z to Z. Well, let's give it identity of type Z to Z. The result will be L of Z, and that's what we want to return. And in the short notation, I can just write it like this, indicating the types. Now the function Q from LZ to this complicated type. This is easier to implement because you're given some L of type LZ, and you return for all a function from some f z to a into L mapped with f. So in Scala, I would write def q equals L going to f going to L map f. Now this certainly will not compile necessarily unless you add some more stuff to this code, but I'll just leave it like this. In Scala 3, this kind of thing would be much easier. In Scala 2, you need to write a lot of stuff to make it look nice. But basically, that's what you need to implement this for all A, and this is not clear, not obvious in Scala 2. It's much easier in Scala 3. But I will just leave that outside of my consideration. I will only look at the code and the proof that I want that. So I defined the functions P and Q, and now I need to prove that P before Q is identity, and Q before P is identity. How do I prove that? So P before Q. So P is applied to some Y of this type. So let me take an arbitrary Y of this type, and apply P to it, and then apply Q to the result. So I define Y prime as Q of P of Y, and I need to show that Y prime is equal to Y. How do I do that? So first let me compute Q of P of Y. So Y prime equals Q, which is this definition, L going to, for all A, F going to L substituted into FL. So Q must be applied to P of Y. So what is P of Y? P of Y is just Y of identity. So if I now substitute Y of identity instead of L, I get for all A, F going to Y of identity, FL. So let us write it a little more easily. Identity substituted into Y, substituted into FL. Now, we know that Y is a natural transformation. So this is an important condition, that we're not just considering any functions of this type. We're considering only natural transformations of this type. This is a very important restriction. So what is a naturality law for Y? Y is a functor Y is a function from a functor Z to A to a functor L of A. So Y and then some function, call it H lifted to L, must be equal to function H lifted to this functor Z to A, which is, I'll just call it like this functor, Z to the type parameter, and then Y. So let's find out what that is, the H lifted to this. We'll find out. It's actually easier to substitute directly into here. So what if we substitute identity into both sides of this law? So it looks like we're getting something interesting, because here we have this Y. In Scala, this would have been identity dot Y dot map F. So we obviously have the composition of Y and map F. So let's call this actually F instead of H. And let's substitute in here. So Y prime equals, for all A, F going to identity substituted into F of this strange thing, and then Y. Now this is the same as substituting directly into Y. So let's compute what that is. So this functor takes, I'm talking about this functor, it's a function, so lifting to this functor is function composition with the function we're using. So identity substituted into this functor is identity after which we compose F. Now this we substitute into Y. Now obviously this is equal to just F So this is the same as y, because this is f going to y of f. This is the same as y. So therefore y prime equals y. And we have verified the first of these equalities. To verify the second one, we start with the argument of q, which is some value of type LZ. Let's call it L. And we compute P of Q of L, and we should show that this is equal to L. So what is P of Q of L? Q of L is defined right here. So it is L, let me just copy that. And so Q is this, so Q of L is this. And now we have P of Q of L. So what is P of that? So I can just remove this for all A, since it's just a type annotation. In the code it does not really occur. P of this, by definition, we have defined as this function. So we need to apply this function to identity. So we need to apply, so this is f going to L, fl, applied to identity. So in other words, identity is now f. So this is L identity L. This is L identity. This is L. Let me make it a little nicer. This is a triangle. So this is equal to L. So in this way, we have proved that these two functions are inverses, like P and Q. And it remains to prove that if we define some y as Q of L, then y is a natural transformation. So let's check that the naturality law of y, which was here, naturality law of y, that it holds. So for all functions f, y, so Q of L, fl equals f lifted to this functor y, which is Q of L. Now Q is defined as this function, so Q of L is f to L f. So let us now apply this to some value, say to value x. Q of L fl equals L f Q of L Lx fl, and then x f lifted to the functor z Q of L equals x and then f, substituted into Q of L, which is xf instead of f in Q of L. So it's L substituted into that xf. So actually I forgot here to lift f, so this is not quite right. Let me fix that. So this is lifted to L, and this is lifted to L. So now I have to prove that L x lifted to L, f lifted to L equals L substituted into xf lifted to L. So this is composition law of the functor L, which makes these things equal. And just make sure that you don't miss this step where I say L substituted into x substituted into f is the same as L substituted into composition xl f to L, and that is equal to that. So this completes the proof of the covariant Yoneda identity. Naturality laws are very often used in derivations of different laws of different type classes. So I'm writing a book which is open source and available at this address, this URL. And in this book, which I call the Science of Functional Programming, I have many derivations, about 100 at this point, with about 11 existing chapters. And naturality laws are used at least about 1/3 of these derivations. So it's a very often used technique where you just learn to recognize you have f lifted to some h and then some function, and then you say, oh, that function is a natural transformation, so this is t and then f lifted to some other thing, and then you continue your derivation. So this kind of thing is very often used. Examples of these derivations, for instance, are the proofs that if you have a composition of two co-pointed functors, then it's again a co-pointed functor. And a co-pointed functor is the one for which you have a natural transformation with this type signature, which extracts values from the functor. Or if you want to show that the product of two monads is again a monad, so the product meaning the pair, just in Scala this would be m of a, n of a, for two monads m and n. Or that the product of two monad transformers is again a monad transformer. So for proving all these things and many other such proofs, you need to manipulate naturality laws very often. And the most useful derivation technique is to write equations and to transform them, just as what I was showing. And the final examples of using natural transformations are inspired by Bartosz Milewski's book, Category Theory for Programmers, where in chapter 10, the book defines the horizontal and the vertical composition of natural transformations. So the vertical composition of two natural transformations applies to transformations of this type, where you have a transformation from f to g and then a transformation from g to h. And this is simply a composition of two transformations as an ordinary function composition. And the horizontal composition applies to transformations of these signatures with completely different functors, so they cannot be composed in the vertical way as ordinary functions. So instead you have this kind of weird composition where you compose functor compositions of this sort. So you compose f to g here and f prime to g prime in a nested type constructor. So in Scala this would be a function with type signature f of f1 of a, say, to g of g1 of a. I'm writing g1 instead of g prime. And for a programmer, this would be relatively straightforward to implement. You first, you know how to transform f1 to g1, that's the alpha prime. And then you just map it over f, so you have first f to f of f1 to f of g1, and then you transform f to g, so you get f of g1. So programmer would have no trouble implementing such a function. So let's write the formula. So first you transform, or you can first transform f to g. So first you transform f to g, that's alpha. And then you get g of f prime, which you need to transform with alpha prime lifted to g. Or you could first transform, so that's alpha prime. So first transform alpha prime lifted to f, so that gives you f of gives you g of f prime, and then you transform that gives you f of g prime, and then you transform alpha. But these two are equal because of naturality, so it doesn't matter how you implement it. So first of all, you need to show that if alpha and beta and alpha prime are natural transformations, then these two compositions are natural transformations as well. And also the book quotes this distributive law. So we define alpha star alpha prime as alpha before alpha prime lifted to g. And so to prove that these properties hold, that this and also this and also so these two are natural transformations and that this holds, we just write out the naturality laws and move things around using naturality laws, because naturality law moves the lifted function around to the other side of other functions until we get the property we need. So I will not go through all of these derivations, just the last one, the distributive law. So let me copy it and go to the next page where I'll just paste it in. And let me also copy the definition of the horizontal composition, just so that I don't forget it. So now let's actually let's make it a little bigger, maybe. Not sure. So okay. So now let me write down this law. Using the definition that I have here, where I will just omit all types, assuming that all the types match, which we can check separately. So the first one, and then the second one needs to be lifted. And the other side, so that was the left-hand side of the law. And the right-hand side of the law is alpha prime lifted, beta prime lifted. So now we use the fact that function composition is associative, so we can just stop using parentheses, and then here we can write out the function composition under map or under lifting. And here we just write this. And we compare what we get. So we got this and we got this. What is different? Only these parts are different. Everything else is the same. But these are equal because of naturality, because beta is a natural transformation. So beta and then lifted something is equal to lifted something to a different functor, beta. Now we trust that the functors are correct because types check, and we're done. In a very similar way, we prove naturality laws for the horizontal and vertical composition. Let me just do the horizontal composition. To prove that the horizontal composition is again a natural transformation, let me assume that I have some alpha, which is, as I had in the previous slide, alpha is f to g, and alpha prime is f prime to g prime. So let me do that. So in the horizontal composition, let me call this U. It is alpha and then alpha prime lifted to G. And by itself, that is a natural transformation, as we will show, f to f prime of I to f to g of g prime of A. So the naturality law for U it is some arbitrary function f lifted to the functor on the left, which is f composed with f prime, and then U equals U, and then f lifted to g composed with g prime. Now, if I just were writing as I did in the previous proof like this, I would get confused because it's a different lifting to lift to just f or to lift to the composition of f and f prime. And it becomes confusing. So let me write out what this means. So it's f lifted to f prime and then lifted to f. U is alpha, alpha prime lifted to g, and that should be equal to alpha, alpha prime lifted to g, and then f lifted to g prime lifted to g. So this is what we want to show now. So let me see what is missing in the proof. Well, we need to move this f all the way to the right. Only then we can show that the two sides are equal. How do we move it to the right? We interchange with other functions. So we can interchange with alpha. Alpha is f to g. Use the naturality law for that. So we have then this is equal to f prime f alpha equal to alpha and then f lifted to f prime to g. So let's substitute that there. So then this left hand side equals alpha f lifted to f prime lifted to g, alpha prime lifted to g. Now clearly we have two things that are both lifted to g. If I just had f arrow here, I would be hopelessly confused. I would not have seen that f is actually lifted twice, and I would not be able to correctly identify the composition law. So now I can identify this two functions lifted to the same functor composed. So that's alpha and then f prime composition alpha lifted to g. So now this I can recognize alpha prime, sorry, not alpha. Now here I can recognize alpha prime goes from f prime to g prime. So on the left it is f prime with the naturality law. So I can rewrite that as alpha prime and then f lifted to g prime lifted to g. Now I have moved f all the way to the right. So let me expand the composition. So alpha prime lifted to g, f lifted to g prime lifted to g. So that's exactly the same as I wanted to show. So in this way you use naturality laws and you prove different properties of natural transformations. So let's see what Bartosz Milewski's book says about that. So this is a composition, and the book does not show the proof that this is a natural transformation. It gives you a diagram for the definition of the vertical composition, but it does not give you the proof that the vertical composition is natural. Now, the vertical composition is just ordinary composition. In his notation, this is beta dot alpha. In my notation, this is alpha before beta. And in his notation, hf. In my notation is f lifted to h. And so then we just have alpha, beta, f lifted to h must be equal to f lifted to f, alpha, beta. Now use the naturality law here. We get this is equal to alpha f g beta. Use naturality law here. This is equal to alpha beta fh here, and this is equal to that. So in this way, in two lines of calculation, we have proved that this is a natural transformation. Instead of doing a long look at some diagram, which this book does not show. It does not show the diagram that you should look at. Because that this diagram is not diagram that will show this. There are no functions f, there's no arbitrary types. It's a much more complicated diagram, which I don't know how to draw necessarily. I will have to spend time drawing it and then looking at it. Instead of looking, you write down these equations and you're done. Similarly, the vertical composition is defined using this. Now it's very hard to look at this diagram and understand what it does. Instead, I had definition, which is just this, of the vertical composition. And for a programmer, this is a very easy thing to understand, how to map nested type constructors, to do nested maps and so on. A programmer will write code quickly to do that. But looking at this diagram and understanding what it does takes a while. And finally, the composition law, interchange law of the two compositions. The book does not try to prove. Instead, the book quotes another book by Saunders MacLean that says the reader may enjoy writing down the evident diagrams needed to prove this fact. Now, so let me show you that even for these 4 lines, the diagram was too hard. Now, in our proof for this interchange law, I used 1, 2, 3, 4 different parts of equation. I'm pretty sure that the diagram would be very complicated and very difficult to understand. And that's why neither Saunders MacLean nor Bartosz Milewski wanted to write down what that diagram is or to explain how to use it. It's very hard to actually use diagrams. It's much easier, much quicker to write down proofs like this in a notation that is quick to use. In principle, however, this notation is entirely equivalent to some code, either in Scala or in a different language. Just that in this notation it's easier to see how you have to manipulate your parts and compositions to get what you want. For example, here it just suggests to me right away that I should use composition under the map. It would not be necessarily as easy to see if you write code. And the fact that this is a superscript also helps because it's visual. It's a superscript aligned with another superscript. You see, okay, this is not the same, but this is the same. This is the same. It's kind of visually easier to see what you can combine with what. So this is why this notation is easier to use. That's how it was designed. So, to conclude, there are other constructions of natural transformations, for example, product of natural transformations, coproduct, exponential, and you can prove that product of two natural transformations is pair of coproduct of natural transformations and pair exponential also give you new natural transformations. So you can prove that using the same techniques as I was showing. And then you have proved that basically any purely functional combination of natural transformations again gives you natural transformations. So you don't really need to verify naturality laws if all you did is combine some obviously natural transformations like identity functions, option, unit type, pair, and so on. So before I conclude, I want to give a summary of the type notation and the code notation. So this is the notation I'm using in my current book. The notation has been checked against many examples and it has proved to be very useful. It covers not only Scala but many other programming languages like Haskell, OCaml, and others that are based on the same type system. It allows you to reason about types in code very quickly. much quicker than if you had to write diagrams or if you had to write code in the code syntax of your programming language, Scala, Haskell, or other language. So these are the notations for Scala. So just to show you what would it be if I wanted to write Scala code for this universal quantifier. I would have to write something like this every time. It would take me a lot of time to write that, and it would make it impossible to quickly reason about it and find the proof. This is an existential quantifier, and basically one after another I just show you what Scala code corresponds to what notation. This notation does not mean any more than the Scala code or Haskell or any other code. It's just a different syntax. And here's an example. This type signature is denoted like this. So 1 plus A, 1 plus B, A to 1 plus B. And similarly with code, I'm not going to go through this. The book explains in detail how to work with this notation. And just to emphasize, this is just a different syntax for the code. It's not some kind of special mathematics that I'm introducing here. I just introduce a different syntax to write code more quickly and to reason about code symbolically in a more convenient way. So I have shown how to use naturality laws to refactor code to obtain simplified versions of some functions, to reduce the number of type parameters. For example, if you remember, the pure method had a type parameter A, but the wrapped unit has no type parameter. And flatMap has 2 type parameters, but flatten has 1. So naturality law is used to show that this is equivalent to this and this is equivalent to this. So this is what I mean by reducing the number of type parameters. You can show that a function with more type parameters, but the naturality law is equivalent to a function with fewer type parameters. So here I do not assume there's naturality law which I crossed out. So there are simpler functions that are simpler to reason about, but they're fully equivalent to others. And in order to show the equivalence, you need the naturality law. I also showed that there's a short notation which is easier to use than diagrams, so you don't look at diagrams, instead you write equations, and it's much more efficient and it has many advantages. For example, if you just look at a diagram, you don't know what you have seen 1 week later. You have no record of what you have looked at. And when you write some equations, you have a full record of every step, what you did, how you reasoned. In my book that I'm working on, there are full details and proofs of some of these properties. I have not yet finished the book, so when it is finished, then everything that's in this talk will be also in the book. Right now it has some material that's not yet written up, and so this talk is kind of just an overview of how you can reason about naturality and natural transformations to get some benefit for you as a programmer.